Okay, we are taking what we used last time reviewing how to use logs to solve exponentials and taking equations that we used last unit. Instead of solving them graphically like we did then, we are going to use our logs to solve algebraically. So for instance, last unit we solved this first equation, finding when that carbon-14 would decay down to 25 milligrams. So last unit we would have graphed the left-hand side is y1 and that 25 is y2 to see where they intersected. Now, however, we can solve this using logs. The first thing that I would do is isolate our exponential, so divide both sides by 200. That gives me 0.125. From there, take the log of both sides so that you can apply your power property. Taking that exponent out to the front, that gives me t times the log of the 0.886 equal to the log of 0.125. Then to solve for t, I would divide both sides by the log of 0.886. From there, enter this on your calculator to get your value of t, which is about 17.18. The next example, we have a continuous model. It says the U.S. population is growing according to the formula given. T is in years since 1995, and what year will the population reach 400 million? So I'm wanting to know that value of t where our population is 400. So I'm going to take that value of 400, plug it in for p to solve. Again, first isolating our base and exponent by dividing both sides by 263. Because this, so taking the log of both sides, applying our power property, bringing that exponent of t down in front, so t times the log of the 1.045 over 1.02 equals the log of 10 thirds, and then dividing both sides by this quantity. When all is said and done, t should equal 49.72 years. Okay, so make sure that you're getting these correct values on your calculator. Okay, next thing that we are going to talk about is what we call doubling time and half-life. It's really exactly what it sounds like. Doubling time is the time it takes for a quantity, whether it's population, amount of chemical, whatever it might be, time it takes for a quantity to double its original amount. Half-life is a similar type of thing. This is the time it takes for a quantity to decrease to half of its original amount. So if you look at the next page, we'll look at a couple of examples using doubling time and half-life. First one asks us to find the doubling time for a bank account growing by 2.7% per year. So we are going to go back to our general exponential function, our y equals a b to the t. We can't solve an exponential equation until we have one. So using what we're given here, we are going to write a function to represent this. With a rate of 2.7% growth per year, this will translate into a growth factor of 1.027 to the t. Now, we are not given an initial amount. We're just asked to find the doubling time. So whatever that initial amount is, that value of a, let's say 1, the output is going to be double that. So double 1 would be 2. Any relationship of that original amount and output of 1 to 2 is going to work here. So if you used 100 and 200, 50 and 100, whatever it might be, as long as this relationship, if this is double whatever that original is. So from here, I can take the log of both sides so that I can use that power property. So the log of 2 equals t times the log of 1.027, and then divide both sides by the log of 1.027. This is what goes in your calculator. We should be getting a t value of about 26 years. On the next one, we are told that 17% of a substance decayed in 5 hours. We're asked what the half-life of the substance is. The difference in this problem is we're not given an hourly decay rate, we're just told how much decays in 5 hours. So the first thing that we need to do is find that value of B, that hourly decay rate. So if 17% decayed, that means 83% or 0.83 of that substance is left, is our output. We used that value of B 5 times. So to find that hourly decay rate, we need to take the 5th root of 0.83. That gives you 0.9634. You have to know that value in order to write our exponential equation. So from there, we have that value of B, but this time we're looking for the half-life. So because we're looking for the half-life, instead of the initial and output being 2 to 1, we need it to be a half of the original. So let's make our initial amount 1, and then the output would be 1/2. From there, I can take the log of both sides, use my power property. I have the log of 1/2 equals t times the log of 0.9634, and then divide both sides by the log of 0.9634. This is what would go in your calculator to find that value of t, which should be about 18.59 hours. Okay. All right, the very last thing that we are going to do is convert between the different forms of an exponential function. So going between the continuous model and then just the basic exponential. You might remember from last unit we talked about the fact that our growth factor B is equal to e to the k. This is the fact that we will use to convert between these two forms. The other thing that we need to know is what k is equal to. If you think about solving this equation for k, what we would do is take the natural log of both sides, and I would have that the natural log of b is equal to k, because that natural log would cancel out your e. So these two pieces of information are what we're going to use for these two examples. So we are given this exponential, we want to write it using the continuous model. What we need here is the continuous growth rate, or k. So I'm going to use the fact that k is equal to the natural log of b. We know that b is our growth factor in the given function, so k is going to be equal to the natural log of that 1.145. You can put that value in your calculator to get that k is equal to 0.1354. And then we're just taking this function and plugging in the values we know. The initial amount at 175, or value of a, is not changing. I'm going to take that and use that again. and then e to the 0.1354, that value of k we just found, t. On the next example, we're going the other direction. What we need here is our growth factor, b. So we're going to use the fact that b is equal to e to the k, where k in this example is 0.3. So if I take e to the 0.3, that will give me my growth factor, which is about 1.35. Taking that, substituting it in that function, using 7 again as my value of a, q equals 7 times 1.35 to the t.